P3A, so basically, so for the project 3, we are basically dealing with memory management. So for part A, again, we will play around with some Linux memory management APIs. For this particular project, we'll do some memory sharings between processes. And for the XV6 part, which is, I assume, the most difficult part across all the projects in this semester, we'll basically focus on the XV6 virtual memory management. So yeah, we'll talk about in details for that part. Okay, so first to start off, let's. I'm not sure if you guys have read through the instructions for P3A. So basically, what we'll do for this project is we want to implement a server, a single server with a bunch of clients. So each server and each client is a process, and we want to share some memories across these processes. Normally, if you have two processes, the address space are not shared, right? Because of the memory virtualization, they have their own virtual address space. So you cannot say so process 2 or process B normally cannot access the virtual memory of process A, right? That's the whole point of memory virtualization. But right now we want to do some magic, not magic, but we want to get help from some particular Linux APIs such that processes can share memories. So some information can be shared across memories. So this is very useful because with this memory sharing mechanism, the processes, the address space are. So basically, the address space of each process is still isolated. Either of them cannot access the other. But when we say shared memory, we have actually a lot of mechanisms. One mechanism we are using here is essentially create shared memory image on very specific, a very special file system, but it's not a regular file system we have. I think we mentioned here, basically we'll get help from the TempFS, called temporary file system, so that we basically put the shared memory page in this temporary file system, and we actually say issue 10 processes and we want to share some particular page, and then we put the shared page here such that every process can access this. So this is what we do here. And I think the behavior of the client and server is simple. So basically each server will basically print out the statistics for each client currently running for every 1 second. And then for each client, yeah, this is some sample output. I will also show you in details how it looks like when we run. And for each client, we'll register basically the shared memory such that the server realizes the existence of that specific process, client, and then also the client will do some printing things. Yeah, so this is basically what we do here. Okay, so let's first to start with some demonstration on how are we gonna have a very simple version of the server, and then how are we gonna have a very simple version of client. So to save time, I have actually already have a very simple code snippet. So let's take a look at the server first. Oops, sorry.
Very simple.
Sorry, not this. Okay, so the shared memory API we are going to use is the first is called sham open. So again, I just now mentioned we will take advantage of the temporary file system. So it is essentially a file system, so we are involved in open some files, right? But right now we are not using the regular open we used in previous projects. Instead, we will use a function called shm_open. You can actually take a look at the menu page of sham open. So it's essentially just as a description, it says just create and open a new shared memory object. So for this project, it's basically a shared memory page. And this function will return a file descriptor so that you can later access it. So it's very similar to what we have in Open. And you can see the argument. So the first argument is essentially the file name for this shared memory page. And here is some like read write, some permission flag. And here mode is like is also similar to the open system call. So we'll use the first API we'll use is sham open, and then we will basically open the file. And here I have a macro here. It's defined here. Yeah, this is my test. So I create a shared memory page called Joan. So just a tip here, and also mentioned in the instruction, because everyone is creating a shared memory page, right? And actually, the page is once you open this, you use sham open, and you will create a file at dev sham. So here there's nothing. This is like system file. Don't care about it. If I run server, then basically we'll create a shared memory page here. So you can see I can run server. And then you can see I just now created a shared memory page called Joan. So everyone essentially will create such file at this place. So an issue is that what if we have like the naming collision, something like that. So we particularly require every one of you don't have random names here. So like just put your CS login so that you will not have collisions. So if you by chance used other people's CS login, and you will have some permission issue, and it says permission denied, something like that. So you just make sure everyone has unique. So since everyone has a unique CS login, so just put your CS login here so that you will not have a conflict. And let's take a look at. So what if I cat this file I created? So I see nothing, right? So the reason is that because right now I just open it, create it, right? But I didn't write anything to that, so that's empty. That makes sense. Okay, the second API we use is called ftruncate. So basically, you open a shared page, but you didn't specify how large is this shared memory region. So for this project, we will just create one page size of the shared memory page. So one page size is like just 4K, so you can specify here. And you use truncate with the file descriptor returned here, so that you will create 4K, the shared memory page of 4K. Well, it's shutting down.
It always shuts down at 6 p.m.
Oh, okay.
This is like an energy conservation feature of the conference room.
Okay, let's just have some have like a 1 minute break while waiting. And it takes forever to shut down. Right. Yeah. Okay. Okay, here we go. Yes. Okay. So just now I said, yeah, we use f-truncate to create desired size for the shared memory. So let's just check if we really create such. So when you type ls-l, you will see the details of this file. You can see this is actually the file size. It's exactly 4K. Okay, so I just created the the shared memory region for one page using f-truncate. Okay, next, which is the most exciting part for this project, we'll use a new function called mmap. Okay, so what is mmap? So I think this function is very powerful, and it's not only just for shared memory region. It's actually just it can be used. So let's just take a look at the menu page of mmap. So originally, it's just creating a new mapping in the virtual address space of a calling process. So basically, you can map this virtual address space to the, sorry, you can map from the disk to this virtual address space, or you can map the shared memory region to this virtual address space. So there are a lot of parameters here. I want to mention, okay, let's just go one by one. The first one essentially is the pointer. So basically the offset of that offset of the virtual address space. So normally you just start from 0. And this is the length. That makes sense, how many sides you want to map. Okay, this bit is called a protection bit. So it's very similar with when you open a file or read a file, you have like the read-only or write-only bit. And the flags here is so the flags here can be either map_shared or map private. So because we're sharing memory, so we'll definitely use map shared. Okay, we don't use map private for this project. And FD is the file descriptor, right? It's returned from the sham open. Yeah, that's basically what it looks like for mmap. Sorry, I said it wrong. So the first argument normally we set it to null, so don't care about it. Okay, and the last argument is the offset. So normally we set to 0. Okay. And this is the size of the mapping. So we want to map one page size, which is 4K, and so for this particular example, I used prot read, which means this shared memory region is only readable to this process. But I think in your project, you should be careful about it. Don't try to just copy this read, and then you probably get a seg fault if you want to write it. So yeah, be particularly careful about this. And okay, definitely we use map shared. Okay, and then now mmap will basically return a pointer. This pointer essentially is the address of the first bit of the shared memory region, right? So normally in the program, we'll get by saying address, we are talking about the virtual address, right? So basically, originally the shared page is on a disk, right, on the temporary file system, and when we open it, and then we use mmap, we map the file on the disk to the virtual address space, right? And then we get a pointer. So that's what mmap do. So after we get this pointer, we can basically do whatever we want. Say, as long as it's within the size of one page size, right? If you go beyond one page size, you will definitely get a segmentation fault, right? So that makes sense. So this is the simplest demo. So this is essentially what the server looks like. So basically, we just so the responsibility for server is to create this shared memory. The client will not create shared memory. Okay, client will just directly access the shared memory and read something or register its detail, so that server can read information from this client. So let's take a look at what client does. So now, because server has already created a shared memory region, how does client?
Joan, she has a question.
Nice. Did you say if the client can write on the shared memory?
Definitely. So I mentioned register. So the client registered the shared memory. I literally mean write information to the shared memory. Okay. Since the server has already opened or created the shared memory page, then how does client get access to this region, right? So again, we need to open this shared memory page. But now we just the protection bit should be read and write, right? Because we will not create client will not create. Server, only server creates. And then again, we use mmap so that we can get that pointer, that virtual address space from this shared memory region. And now for line 16, let's see, what does this line do? So basically, we create a char character, and then which is the string hello world, and then I do string copy. So basically, I copy this string to this this pointer. What does this mean? What does this do? So essentially, we just write the string hello world to this shared memory region, right? Because the shan pointer is the virtual address space, the first bit, the first byte of this shared memory page, right? And we copy this string to the address of the first byte. Means we write this string to this shared memory page. Does that make sense? So unlike read or write system call, so for this project we don't use read or write. So how are we gonna read or write information to that shared memory region? We just directly either use like string copy, or you can assign a specific character to each byte. Okay, so we just use either the assignment or the something like string copy. we don't use the specific read or write system call, because this is, after all, very different from the regular file system I/O. Okay. Okay. Now let's try to run these two processes, one server and one client, concurrently. So the idea is that, well, let's go back to the server again. The idea is that after server creates this shared memory, and it just sleeps for 5 seconds, and meanwhile, the the client process will write something, write the string "hello world" through this shared memory region, and after it wakes up, it prints down waiting for the client, and then tries to print if something already is written to this shared memory. Does that make sense? So normally, if we don't open the client at all, we just run this server, we will print nothing here, right? Because there's nothing in the shared memory. But now we just open another process, which is the server, which is the client, and client writes the string to the same shared memory region, and then the server will definitely see that and print out. Okay, now let's just okay, let's again, before doing that, let's just, I just want to make sure that we have nothing, right? We have nothing in this shared memory region. When a cat is just nothing. Okay, now let me just try to open another terminal. Oh, by the way, when you run multiple processes concurrently and you want to share the memories across these processes, you have to make sure that all of these processes are issued at the same machine. If you have login using best Linux, then by chance you will machines, then you can definitely not be able to share memories across different machines, right? Okay. Let's wait a sec. So it's P3. Okay. Okay. Let's try to compile. I think it's already compiled, but just let me compile it again. Okay. Yeah. So the issue is that. So see, it doesn't recognize shen open, so don't panic. You can just, so it says you have to link with this guy, okay, when you compile. Ah, sorry. Let me do that again. So it's RT, okay. So, okay, and let's compile the client. Okay, now let's just open the server, and immediately let's open client. Okay, the server done waiting and it says hello world. Okay, and now let's take a look at the shared memory page. There's a hello world there, right? Because it was written from the client. Is it happening too fast?
When did you run the client side?
Okay, let me do that again. Okay, let me just remove this. Let's just remove this. Let me do that again. Okay, so I've removed this shared page. And now I run server first, and then immediately I run client at the other. And now let's go back.
Do one in the background if you're doing it in the same terminal, or does that not work?
Sure, you can do that in the background. That's a good idea. So let's try again. Okay, remove and server and put it at background, and then client. Five seconds later, yeah, we will see this. This is out. Yeah, yeah. So yeah, so the 5 seconds is just I hard coded, but yeah. So here we have done waiting and hello world. and you have something in the shared memory region. Let me see there's a hello world here. Okay. So this is a very simple demo, but hopefully that makes sense. Questions?
Who would be responsible for cleaning up?
Definitely, that's a good question. So for this demo, I didn't do any cleanup, so I have to manually remove every time I run. So in your project, you have to definitely remove this shared memory page, but that's happening after you close or terminate the server. So every time you close server, you have to clean up the shared memory. But if somehow, because we can have multiple clients come and multiple clients gone, clients leave or come doesn't matter. But if the server terminates, you have to clean the shared memory page. And how to clean that? You just use, I think it's sham unlink. So I think it's also at sham open. So I think it's it's kind of so here, yeah, there's a function called sham unlink. So you use sham unlink to remove the page, remove the object created by sham open. Okay.
So if you were to just run your client right now,
Oh, you mean if I didn't open the server, I just
does it like fail gracefully, or I mean, you need to make sure that we can't create servers.
so if there is no shared memory page created at all, I only run client. For my demo, I think I will get segfault, or probably not segfault. Probably I will return. Let's just try. I think the file descriptor will be -1 when I do sham open. Yeah. Oh, and segfault.
Oh,
Right. So it's not exiting gracefully for this demo, but for your project, you have to handle this. Yeah. Okay. So.
Do we have to handle that though?
Sorry.
Should we? Oh, okay.
Okay. Sorry, I think I probably fall behind the schedule, but yeah, I think I. What is this? I think I accidentally. Okay. Okay. So I think the most difficult part for this project is because we used some knowledge that is slightly advanced from the lecture. I mean, because from the lecture we will talk about the concurrency, especially the logs or mutual exclusion. If you don't know this terminology, that's totally fine. But for this project, we will somehow use this idea. The reason is that because we are issuing multiple processes, right? These processes will run concurrently. So there will be an issue. The issue here is that, so okay, let's just try to, I'm not sure it's, because if I write something here, probably it's not good for the students watching the video, so probably I'll do here as a so basically I'll just try to mention the shared memory layout. Okay, so basically we have one page, right, which is 4K. So, and as it was mentioned here in the, we will support some, there's an up limit for the number of clients. So I think it's 33. Yeah, the server must be able to handle 63 clients concurrently. Why 36? Is that we want to divide this shared memory region into 64 segments. Okay, so each segment essentially is I think it's 64 bytes, right, for each segment. And then we will basically reserve one segment and use the rest of the 33 segments to register to basically record or keep track of the stats of each client, right? So basically, each client will register one segment, register its own stats to that specific segment, such that there will be. So if say client A is just segment 8, for instance, then this segment is only for process A. I mean, no other process is able to enter this segment. That makes sense. Otherwise, you'll get messy information, right? So basically, each client has its own segment reserved for. And after this segment terminates, and we will just clear this segment such that later new client can reuse this segment. We don't want to have like memory leaks, right? This is, if you don't clear this segment, it potentially creates the memory leak, basically. So we have to clean up this segment when this client leaves. So I think so far so good, right? Because every client, when it enters, it is basically assigned to a specific segment. We don't have like the race condition, or we don't have the content across processes, right? Then why are we still bother using the so-called clock or mutual exclusion? The main concern is that when the process, when client enters the pool, it has to select one segment, right? You can just select sequentially, find the first available segment, and then use that segment. However, if there are multiple clients trying to enter this process basically simultaneously, then there will be a race condition, right? Say if there are 3 clients entering this pool concurrently or simultaneously, which segment we will assign? If you use the first available policy, like you find the first available segment and you assign that segment to this client, then essentially you will basically say the first available segment is like 6, then multiple clients enter the pool almost simultaneously. And if the first segment is 6, then there will be trouble, right? And essentially, then all these clients will potentially be assigned to to seg6. Right. So we have to make sure that although they are entering the pool simultaneously, we still have to use a specific technique to make sure that we assign them one at a time. That's basically what we do here. And how are we going to do that? We'll just use something called mutual exclusion. So literally just means we have to make sure that the event happens one at a time instead of concurrently. So, or you can say it's a lock. So when, as long as a specific process client enters the pool, and we make sure that only one process acquire this lock or acquire this mutual exclusion, and if it acquires it, then other processes or other clients are no longer able to acquire this lock. They have to wait outside until this specific process release the lock. So that's basically what we do here. And you just want to protect this region. So you use lock to protect the instruction. What instruction? It can be happening, well, it's very implementation specific, but you have to make sure that you have to protect the instruction where you assign the segment, basically. And how you assign a segment, I think you can come up with an idea. I just don't want to spend some time explaining here, but I think it's a very easy idea. And you have to, there are basically multiple ways to do that. But basically, you have to use the lock to protect this instructions where you assign this assignment, assign this segment to the client. Okay. So how to use this lock? Actually, it's very simple. First, okay, specifically, this lock is called semaphore, but if you don't know it, that's fine, just the terminology. Gerard will talk in details for the next chapter, but right now you just take it as a terminology, as a simple mutex lock. And then you first initialize the lock, okay, the mutex. The argument just, again, can take a look at seminit. So again, it's you have to, before that, you have to include the semaphore.h, and then you initialize the lock. You can see the second argument, which is very important. It's called pshared. You have to set it to 1, because if it's 1, then it means the lock is shared across. Okay, if it's 0, then it's shared across threads. But if it's 1, then it's shared across processes. Because we're sharing between processes, so we definitely use 1 for this argument. And for the value, just right now, you just use 1. That's fine. Okay, then, okay, first initialize it, and then okay, and then when you want to acquire the lock, you will use semWait. And when you release the lock, you will use semPost. Again, you want to see the menu page of semWait and semPost, but they're basically very straightforward. So basically, I think I can show you, I've shown you the skeleton code, right? You can start from here. So basically, you will do, right here, you initialize the semaphore, which is the lock, and then probably this is the server. Take a look at the client. Okay, so here, so basically, whenever a client enters the pool, you have to, so basically, this is the critical section, right? So each you wait for this mutex, which means it acquired the lock. And then your client will search through the segments to find a valid or available segment, and then mark this segment as invalid, which means other client will no longer use this segment.
So
Basic, sure.
the init happens in the server. You don't have to initialize it here.
So yes, so the initialization of semaphore only takes place in the server. You don't want to initialize the semaphore in the client. Okay, so the initialization should only happen once. You should not initialize it multiple times. If you do that, you'll get very weird bugs, so don't do that. You only initialize once, which is only at server. And for client, you just use this as a lock to protect the section where you assign the segment. Okay? You will do this here. And then you enter a while one loop. Print out the information every 1 second. That's it. Okay, by the way, I haven't... So again, just now I said that we divide this region into 64 bytes, right? And why are we only supporting 63 segments instead of 64? The reason is that we want to reserve one segment. One segment, which is for the mutex, right? Why? Because the mutex itself has to be in the shared memory region, right? Otherwise, if it's not shared, then there's no use. So only when mutex is shared across process and across processes can it have effect on the locking, right? Otherwise, the lock would not work. So basically, we'll reserve one segment for that mutex, and the remaining 63 are used for. So each segment is used for the statistics for each client. Okay, so that's briefly introduction for this part. And actually, there's another tiny bit of this project is the signal. Because, okay, before I talk about that, I just want to try to show you guys how does this project finally looks like. So I'll just open the server first. Okay, when I open the server, nothing happens because there's no client. And now I just open one client. And for client, we will output, for each second, we will output currently active clients, which is itself. The number is PID. Okay. So currently there is only one client, which is itself. Makes sense. Let's go back to the server. You see, for the server, it just prints out the information every second because there's only one process, only one client. Okay, and how are we gonna terminate this client? We just use Control C. Okay, so just now I said because we use Control C. Control C actually means a signal. When you type Control C, you send a signal to the program. So in your server and the client, I think it's client, you have to write a signal handler. You have to recognize, okay, when I type Control C, it means this client should terminate. So that's why we have also write the signal handler. But I will talk that in details later. Right now, I just want to show you how it would look like. Okay, when I kill or terminate the client, and you can see the server no longer print anything, just print a bunch of white space. Now let's just try to create a new client. Okay, another client enters. Okay, it's got a new PID, and now the server begins to print new things. Okay, now let's try to run two clients concurrently. Or probably three. Okay. Now you can see each second, now there are 3 clients active, right? And now here in the server, you can see each second we have three processes. And if I try to kill one of them using Control C, okay, now we only have 2 left, right? And then we have 2 left here. So that's basically what this program looked like when you run. Okay. So because I put these 2 guys in the background, so when you put it to the background, you can no longer type Control C to kill it, right? The only way to do that is using kill PID 14003. Okay, kill 1 and 4. Okay, and now you'll see nothing here. Okay, and finally, when I try to kill terminate the server, I just again type Ctrl C to kill the server. Okay, so how are we gonna send this signal, Ctrl C, or actually when you kill, right? I think when you do P2A, you say kill is actually sending the signal, right? When you also type kill PID, you are actually also sending the signal to the process, saying, okay, you have to terminate. So how are we gonna handle that? We just have another piece of snippet here. So basically, at the very beginning of your main function of the client, you do a couple of things here. So this is actually just a struct called seekAction. Okay, definitely before doing that, you have to include signal.h. And then you set up the seekAction handler as HD, which is defined here as a function. So in here, you will do whatever you need to do on the exit of the client. So normally, when you I think I mentioned just now, when your client exits, you have to clear this segment, right? So such that later new clients can reuse that segment. So this is happening here. You have to basically clear up the segment on exit, and then you can go ahead sending the signal with like seekInt or seekTerm. So seekInt, I think there's a table on Wikipedia. You can seekInt or seekTerm. There is a list of signal. Right. So there are multiple signals here. So probably we are only interested in the seekTerm. Just terminate the signal. It's usually sent by when you type kill in shell. It sends seekTerm to the process. And seekInt is here, terminal interrupt signal, which is Ctrl C. Okay, I think these 2 are fine. Oh, you can surely also include seekkill if you want. But yeah.
Is that a one of those 3 or all of them?
So each
any one would do it?
So if you only have seekInt, for instance, then you do kill in the terminal, you will not send signal to your client. So they are matching, right?
So it's the different signals.
Right, different
kill
signals.
versus the control C.
So every time you, yeah.
So we should handle.
So this each signal corresponds to the different, that's basically what we do here. And I think it's very clearly written in the comments of here. So at the very beginning of your main, you have to do the signal handling. Use seekAction, and then you have to and here specifically at the exit handler, you have to make sure that the segment is cleared. Right? Oh, by the way, this is also a critical section that you need to protect by the mutex or the lock, because just you have to also use mutex to protect this region. Okay. that's it. Okay.